Hello, this is Dhavide Aruliah from QuantSight, and welcome to today's lesson on tuning Dask data frame performance. So, as an outline of what we're going to do, we're going to take a look at a particular data set that comes from peer-to-peer loans, and we'll use that as a motivating example to look at some Dask data frames. We'll review the structure of Dask data frames and how those extend what we know from using Pandas. And we'll look at two particular strategies for improving the performance of using Dask data frames for data analysis, in particular using specialized binary storage format like Parquet, and also using categorical variables in order to make storage more efficient. So the Lending Club dataset is a particular dataset that comes from peer-to-peer lending platform. It's gathered over about an 11-year period. There's roughly 2.25 million loans with features drawn from particular properties of particular borrowers. So to start, we'll do some generic sort of Pandas imports, and we'll then define, using the path library, particular convenient shorthand for paths for the data files that we'll be looking at. So in particular, there's a large comma-separated value CSV file called lendingclub.csv, and we'll also be using a subdirectory called temp_root for storage later on. The advantage of doing things in this particular way is our notebook is then sort of more device independent, operating system independent. So we can write here, for instance, a little function called MB size that we apply to the CSV file object, and we find that that CSV file is about 300 megabytes in size. Right? So the advantage of doing things like this is that everything is operating in this system independent. We'll find this particular file, about 300 megabytes, that fits easily within memory on my laptop. But the advantage of using Dask in the way that we'll be doing here is this could extend in principle to having a whole folder full of many files or very large files independently that can be treated in chunks using Dask data frames. So we'll use the Pandas Read Csv function just to load this into a data frame. Notice I'm using the %time IPython magic, and that takes about 5 seconds because each of the rows consists of strings of characters that need to be converted into various kinds of data types. So for instance, when we use the tail method to examine the last 2 rows of that data frame, we see that there are a sequence of columns with names like loan status, issued date, loan amount, and so forth, of various different data types. There's 22 columns, most of which are numerical values, but some of them are strings that are in fact refer to certain kinds of categories. And there's also one column that is a date time type. Notice there are also some missing entries that are filled in with NaN or NaN, which is a common thing. We also see from the index values that there are which are just numbered in increasing numerals, increasing integers. We see there's about 2.25 million, basically, a little more than 2.25 million rows in our data frame here. So the columns of our data frame are things like the loan amount or the annual income, which are mostly numerical kinds of values. But there's also a few which are categorical features like the loan status, which can be charged off or current, or the term, which is either 36 or 60 months, which is in fact categorical, even though those in principle you might think of those as being integers. There's also the issue date column, which is a date time. So all of these get encoded in slightly different ways when we actually load them up. We can look at the schema using the .dtypes attribute, and we end up then with a Pandas series, and we see that all of the categorical columns are encoded as objects, which really means string in this case, There's the numerical columns are mostly 64-bit floating types. That's partly because some of them are have missing values. So even if they're integers, they would get encoded. The missing values would probably be encoded as a nan. And these object columns are actually strings, and they need to be read from the comma-separated value file, the string, which is actually quite inefficient. And much of what we'll learn about today is how to compensate for that kind of inefficiency. So let's remind ourselves about what conceptually a Dask data frame is like. So it's really a collection of individual Pandas data frames. So even though I'm looking, say, on my laptop at what I think of as a very, very tall and narrow data frame, it's actually represented as a section of as a collection of chunks or partitions, which are smaller data frames that are represented in memory either on my laptop, or it could be conceptually there are individual workers in a cluster, each of which is storing one of those partitions. And the idea is for us to, as users, to pretend we have a Pandas data frame that is just really massive, that is distributed amongst all of these different workers, so that we can do manipulations using our standard Pandas idioms. So this allows us to work with data that would be too large to fit on a single machine, i.e. on my laptop, and those individual chunks or partitions can exist in the memories of workers that are distributed. And in principle, this also means that we think of these as being many different data frames that are stacked one on top of each other. So in particular, we're assuming that there are many, many, many more rows than there are columns. The number of columns should easily fit within the memory of a single machine, whereas the number of rows, if we tried to store the whole thing, might actually choke our machine. So when thinking about high-performance computing, this is a useful picture to have in mind, the hierarchy of computer memory speeds. So if we look at the top level, we have the CPU, or the central processing unit, which typically is able to do billions of operations a second. A single clock cycle is usually on the order of a nanosecond. By contrast, if you're fetching data from the memory into the CPU to do work on it, it might be stored in what's called the cache, which is some fast memory that is local to the CPU, or it might be in the RAM, the random access memory, the main memory, which is larger but typically slower. So the cache access might take a few dozen nanoseconds. Getting things from RAM might take on the order of even a few microseconds. So, tens to 100 times more in terms of what a CPU cycle would be. By contrast, if you're trying to get things from disk, that will be much slower, typically on the order of several microseconds or even milliseconds, and getting things from networks will take generally milliseconds in sort of time scales. A particularly important distinction to remember is when working with Dask is that this memory hierarchy is useful because disk access is typically very slow and network access even worse. So trying to get data from a hard disk drive which has magnetic spinning platters, or what's more common now is a solid state drive like we have here on the right. Those are much faster drives, but even still the access times are typically on the order of microseconds to possibly milliseconds with hard disk drives. And those are really much slower than getting data from RAM by orders of magnitude, by hundreds to thousands of times slower. And that's what makes a difference when we're actually working with Dask data frames. And we'll see this some more in some timed experiments coming up. So in particular, to bring this back to our Lending Club data, so we have comma-separated value CSV files with text entries in some columns that are costly to store and to read. So we'll look at a specialized storage format called Parquet. There are many different storage formats, but we'll just use one that's particularly popular now, called Parquet, as one means of improving the efficiency of storage and also improving, by consequence, the efficiency of data access when we're getting things from disk. But we can also look at categorical storage as a means of improving efficiency for storing some of those categorical data. So for a start, let's actually use the Dask data frame reading methods. So this is very similar to what we did before. We have a function called Read Csv stored in the Dask.dataframe module, which we've aliased here as DD. We'll use the same CSV file, that identifier we had previously, and we'll also use the parse dates equals a singleton list with issue underscore D. Whoops. Let me make sure I get this in the right. There we go. So that's a singleton list, and make sure I spell parse dates correctly. So when I execute this and I look at df underscore CSV and I try and time this, it returns immediately, and I can see the wrapper for this particular data frame. So notice that took 0 nanoseconds on this Windows operating system. My Linux system would actually be a little bit more, has probably more refined clock cycle that it will return to me. So again, let me just do that again. And we see that we don't actually load this data frame into memory. It returns immediately because it's not actually loaded, and we just get a sort of a quick overview of what the structure of that data frame looks like. And notice it also says n partitions equals 5, which means conceptually it's being treated as 5 different chunks. We can visualize these chunks. We can visualize the computation associated with this object df underscore CSV using what's called a task graph. So this task graph here shows us 5 different separated chunks that with this read CSV function call and this square block that refers to data, and this is the flow of data from each of 5 different chunks of this large file that are being read into separate areas of memory, which in principle can be operated by different workers, different threads on my laptop, or different processes if I have a cluster which can distribute this to different workers. So if I call the tail method associated with the Dask data frame df underscore CSV, an actual computation is triggered. So I'll use here the %timeit magic from IPython that will repeatedly do this computation. It looks like it did it about 7 times, and those computations averaged about 962 milliseconds in each of those loops to just read the last chunk and display those. I guess we didn't display those because that was hidden inside this. We could do that in a separate line. But it took about a second to do that, so that's actually quite a bit faster. So if I compute the mean of a column of a data frame, so what I'll do here is I'll take my data frame df underscore CSV. I want to extract the lone amount column, and I want to apply the mean, and I'll store that in an object called result CSV. So if I use the time magic to work that out, and I just look at result underscore CSV, it returns initially as what's called a Dask scalar object, and it's unevaluated. So for most Dask objects, remember what we have to do is we have to use something called the compute method to trigger an actual computation. And when that is actually done, this actually involves going to disk, reading the file into a whole bunch of different workers or threads, then we can extract that lone amount column and compute that mean and see what that looks like. So to visualize that computation, here we have a task graph illustrating that whole thing. So notice this computation graph or this task graph is quite a bit more complicated than the one we had before. And notice these disjoint branches down in the bottom here actually correspond to these disjoint branches correspond to work that can be done separately, and where they join around the middle is where we can actually have we have communication required between the different workers that actually needs to be coordinated. And so that's sort of a bottleneck in that, and with the opportunities for parallelism are more down near the bottom. There's a little bit after this aggregation, but really those are all being done with much less data, so it's quite a bit faster. So having seen how Dask can be applied with this data set in general, let's see about how we can improve the efficiency by, instead of using comma separated values, which is very nice because it's human readable, let's use an open source binary storage format called Parquet. So in Parquet, columns are stored contiguously on disk, which is more efficient for things like Pandas data frames, because in Pandas data frames, naturally, the data is all of the same data type along all of the columns. So each of those columns, they can be compressed and stored on disk, and they're separated into several files so they can each be worked on for parallel processing. So as an example, let's actually take, we still have this df_csv in memory as a Dask object. So let's take that CSV data frame object and let's export it to Parquet. And there is a Pandas and Dask method associated with data frames called toParquet. We've created an object in memory called Parquet path, which is just a path lib object. Again, it's done in an operating system independent way that'll point to what will end up being a folder called lending_club.park. We have to give a computation engine, and we'll use the fast Parquet computation engine as a means of computing the Parquet, doing all the transformations from the CSV. Now this should take a few seconds to run because it has to read all the data from the CSV. It has to do various operations that include compression. So it took about 6.5 seconds there to do that. But if I look now, I should see I have a new folder that's called Parquet path, which was whatever that was called. I think it was lending_club.park. And I can look, in fact, that has a sequence of files in it. There's about 5 different files, each of which is about 75 megabytes in size. So remember, the whole thing, the whole data set originally added up to 300 megabytes. So this is a little bit of an improvement, but not much. This is, again, I guess, about 225 megabytes in size, so that's actually not bad. So we can now take that file that we've just created and we can actually read data from it, right? So just as there is a read CSV method, there is a read Parquet method. And again, as is typical in Dask, the Dask.DataFrame module, we're mirroring a Pandas function. So there's a Pandas function with exactly the same name, and it has a similar syntax, and in fact, we can, and again, we have to specify the fast Parquet engine. And when we look at the wrapper, we see this is very similar to the wrapper we had for df_CSV, the Pandas, the Dask CSV data frame that we loaded. But this is now associated with these, with a Parquet store instead of the CSV file. So this means we can basically do the same computation we did before, right? We can extract the loan amount column, compute its mean, and then call the compute method and see how long that takes. And then of course we can do the same thing with our Parquet store. So df_Parquet is a Dask data frame that is associated with the Parquet store instead of associated with the CSV file. And that means we can compute this new result and notice that takes 239 milliseconds instead of 2.5 seconds, which is about a factor of 10 improvement, right? Which is quite good. We can visualize this tree, and this is exactly the same tree we had before. The only difference is we're reading from a Parquet store instead of reading from CSV file. So that's pretty cool. We've done a little bit to improve this. We've seen how Parquet, using Parquet files actually improves the efficiency. But if we look at that Parquet Dask data frame that we have associated with the Parquet store, notice these columns are still being read as objects: the loan status, the term, the address state, and various others. So there's still more room for improvement. And what we can do is we can use Pandas categoricals to replace these object D types efficiently. So those will use integers instead of strings to represent the different entries of these categorical columns. So there'll be a little bit of startup time to do this transformation, but if we can store that into our Parquet store in the first place, then we get better storage and we also get better amortized performance in the long run. So let's take a look at how we can do this. First, what we'll do is we'll use that dtypes series. We'll extract all the columns of type object, and we will extract that subset of the columns to get an indexed data structure. It's just a generic index data structure that we have from Pandas data frames that has the categorical columns in them. So there's 4 different columns: loan status, term, address state, and home ownership. So if I look at, say, the term column and I apply the unique method to the series we extract from that column, and I apply compute, remember, because this is a Dask computation, I can see that there are 2 different unique entries in there, 36 months and 60 months. So even though in principle those could be represented as integers, in fact what we'll do is we'll just treat it as a categorical, and there's only 2 different values. And rather than having to store all of those characters in the string for each entry in the column, we only need to really represent those as the integers 0 and 1, because there's only 2 different values. By the same token, we could look at the home ownership column, and let's time this computation, right? Because this involves reading from our Parquet store again. So that took about 580 milliseconds to extract the data from the Parquet store, to look down that particular column, find all of the unique entries, and notice there's about 6 different entries in that column. Now notice though, if we had actually just looked at a particular sub-block, one of those chunks that we have in our Pandas data frame, our Dask data frame consists of, remember, a collection of different Pandas data frames. In partition 0, we only have 4 of those different categories arising, not all 6. Right, so the home ownership, we have mortgage, rent, own, and any, but we don't have none and other, which maybe is a flaw of our encoding scheme, but we will see. Right, so the moral of this particular story here is that when we have a Dask data frame, we have to be a little bit careful dealing with categorical types, because not every particular category is going to occur in each chunk. So for the home ownership column, that was we just saw that there. But remember, if we had another column that was called address state, which would correspond to the 50 different states of the United States. So in each one of these different vertical chunks, we might not have all of the 50 states occurring in all of the entries, depending on who was borrowing from what states. There's different populations in different states. So there's normal reasons why that might happen. So there is a method called categorize associated with Dask data frames that does not correspond to a Pandas function, where we have to scan the entire column to read all of the categories. And then what that does is associates with the Dask data frame, it associates some metadata with that particular column that can be shared with all of the workers, so all of the workers will know all of the particular categories that are associated with a particular categorical type. So the way that we can get this information out is we can do something like this. We'll take our Parquet data frame and I'll assign I'll apply the categorize method to that. By default, if I don't put any arguments, it will apply to all of the all of the categorical columns, but since I've actually identified what those are, I will actually just put those in explicitly. And when I do that, it takes a little bit of time, but now what has happened is all of those columns that were formerly called object are now called category, so they're stored more efficiently, and different comparisons and different kinds of access and computations with them can be done marginally more efficiently because we don't have to move strings around. We only have to move integers, which can be moved more efficiently. So in particular, if I take a look, I can examine the first few rows of my new categorized data frame, and I see these things. They use the metadata. These are really stored internally as integers, but the strings associated with each corresponding integer are known to the whole Dask data frame, so I can view those by whatever the original representation is. So those aren't, whether or not that's an abbreviation for a state or an or 36 months or 60 months for the term column and so forth. So I can look at, for instance, the term column that has two categories. Notice that that was returned immediately. It didn't have to do that extra processing because this index here, this data structure associated with these categories is stored associated with metadata with the Dask data frame. By the same token, we have all of the categories of the loan status are stored in the metadata now that I've categorized this data frame. So let's actually capitalize on that a little bit more. Let's make a new place for a new Parquet store, and we'll use the same command we did before. We used a toParquet method to take this data frame that we have loaded from Parquet, we've categorized it, and now we're storing it back to disk. So if I look now in my new path, we have some smaller files. Remember before they were about 75 megabytes, now they were about 50 megabytes in size each. So we've got a little bit more efficiency. We can read those from disk, and we can do a computation in about 80 milliseconds, which is pretty good. And again, we can see that the categories are associated with categorical data types in the columns that actually had objects formerly. And again, we can sort of take a look at the last few rows, and that was a pretty quick access as well. Now that I'm, even though that did involve sort of reading that from disk. So one caveat we have to recognize though is that categorical data types need to be statically known to Dask. So even when I've read it from disk, it still needs to actually know what all the categories are. So for instance, there's an attribute called known associated with a categorical column. So since I had read the Parquet file and called the categorize method, that attribute is set as known is true for df_parquet_cat. if I look at my new data frame, df underscore parquet underscore new, that same attribute is false, even though we stored those as using that categorical type. And that's because until I actually load these things from disk, that data isn't known which categories are in which partition. Each partition is going to have its own, again, just as we saw before, not all of the categories are going to occur in every chunk. So the way that we have to get around that is we have to call, and if we try and extract the categories from df underscore parquet underscore new, they're not, because that known attribute was false, we get an error when I try to look at what those categories are. So the way around this is to call the categorize method again. But if it has been stored as in categorical form, that actually occurs very quickly. And then this attribute is true. And so as a result, we are actually able to extract the categories from, say, the loan status column without having an exception raised. And again, we can see the structure of this. Right. Remember, if I call df csv, that only is really just reading from disk, and the same structure of task graph we will get for df underscore parquet and parquet new. And if I look at, after calling the categorize, there's an additional call to the categorize function, categorize method, which has to be done on each block, but those can all be done in parallel. Afterwards, there is some communication back to the metadata of the whole Dask data frame. So as one last step, let's actually do a slightly more complicated computation. So as a last exercise, let's actually do a group by. So we'll start off here with df underscore csv. And we'll do a group by on the loan status column. We'll extract the loan amount column from each one of the groups, and then we'll compute the mean. Right? So if I do this, of course, this will return instantly because I haven't done the compute method. If I call compute, now this is reading from CSV, so this should be relatively slow because remember, it needs to read each row of the CSV. It needs to parse each of those strings, store those as objects, and then it takes about 2.6 seconds to do this whole thing. Let's try that again using our Parquet. So but this is the Parquet that is uncategorized. We didn't do the storing the categorized columns. So that still took a little bit of time too, because it still had to do working with strings. It had to read all those strings from disk and work with those in order to do the group by. But now let's see what happens if we actually do the same thing with the data frame if it has been stored in a categorized format. And this time we used the time it magic. So that took about 700 milliseconds. Now we'll use that same data frame again, but we'll apply the categorize method to it after we've loaded it, and then do the group by. And this is taking a little bit of time. So that actually took 3.7 seconds. So that was actually rather long again, because it was reading the strings from disk first and then applying the categorize method and then having to do that group by. Whereas now let's do the case where we've got the pre-categorized Parquet store. And so all we need to do is just do a little bit of additional cost. So there's the slight little bit of overhead of actually doing that so about 75 milliseconds to do the call to the categorize method, but it's still quite fast. So in summary, storage formats affect performance significantly. So we can do clever things like using Parquet and using categorical variables to improve the efficiency of storage. That can make a big difference in terms of the performance that we get, changing, say for instance, a 1 to 2 second wait time to something on the order of 70 or 80 milliseconds. So huge gains can be made when we just learn how to combine clever storage formats with our data workflows with Dask data frames. So thank you very much. I hope that you've enjoyed and gained something valuable from this lesson.